Have you ever wondered where stars, those twinkling lights in the night sky, come from? Our journey begins in the vast, cold void of space, in regions you might not expect stars to be born. These regions are known as nebulae, immense clouds of dust and gas, primarily hydrogen and helium. They are the cosmic nurseries where stars begin their lives. Now you may be thinking, how does a cloud of dust and gas become a star? The magic ingredient is gravity. Gravity, that unseen force that keeps our feet firmly planted on Earth, is at work in the nebulae, pulling these particles of dust and gas together. As these particles come together, they form what we call a protostar. The protostar is a bit like a baby star. It's not quite a star yet, but it's on its way. Picture it as a growing ball of gas and dust, becoming denser and hotter as it continues to accumulate more and more matter from the nebula. The center of this protostar, its core, is where the real action begins. As the core continues to heat up, reaching temperatures of millions of degrees, something incredible happens: nuclear fusion. Nuclear fusion is the heart of a star. It's the process that powers the sun and every other star you see in the sky. In the extreme heat and pressure of the star's core, hydrogen atoms come together to form helium. This process releases a tremendous amount of energy in the form of light and heat, causing the star to shine. With the ignition of nuclear fusion, the protostar has finally grown up. It has become a main sequence star, like our sun. It will remain in this stage, shining brightly for billions of years, providing light and warmth to any planets that might orbit it. So the next time you look up at the night sky, think about how each star began its life in a nebula. And remember, every star you see is a testament to the incredible power of nature, the force of gravity, and the magic of nuclear fusion. Now that we know where stars come from, what happens next in their life cycle? Once a star is born, it enters the main sequence phase, which is the longest stage in a star's life. This is the star's prime time, if you will. It's when they're at their most stable, and they can stay in this phase for billions of years. So what's happening during all this time? Well, deep in the core of the star, a process called nuclear fusion is taking place. This isn't just any old chemical reaction, mind you. This is the process that powers the sun and creates all the heat and light that makes life on Earth possible. In this fusion process, hydrogen atoms in the star's core are being squished together under immense pressure and temperature. When they combine, they form helium and release a huge amount of energy. This energy is so powerful, it creates an outward pressure, pushing against the weight of the star's outer layers. Now you might be thinking, well, that's all well and good, but why doesn't the star just blow itself apart with all that energy? That's a great question. This is where the delicate balance of the universe comes into play. While the energy from fusion is pushing outward, gravity is pulling everything inward. These two forces are in constant competition, maintaining the star's size and keeping it from either blowing apart or collapsing in on itself. This is what we call hydrostatic equilibrium. It's a little like a tug of war, but instead of two teams pulling on a rope, it's energy and gravity pulling on a star. And just like in a tug of war, the star stays in the middle as long as both sides are equally strong. This balance, this dance between gravity and energy, is what keeps a star shining for billions of years. It's a testament to the intricate balance of the cosmos and a fundamental part of the stellar life cycle. This balance, this dance between gravity and energy, is what keeps a star shining for billions of years. So what happens when a star runs out of fuel? This is a question that has intrigued astronomers for centuries. The answer, as it turns out, is not only fascinating but also illuminating about the nature of our cosmos. When a star has used up all its hydrogen, it doesn't just flicker out like a spent candle. No, the star goes out with a bang, not a whimper. It starts to contract under its own immense gravity. As it contracts, the core of the star begins to heat up, and the outer layers start to bloat and expand. This transformation turns our once shimmering star into a red giant. Now picture a red giant. It's a celestial behemoth, swollen to hundreds of times its original size. These giants of the cosmos are often visible to the naked eye, their reddish hue a telltale sign of their advanced age and impending demise. But the story doesn't end here. As the star continues to contract, its core gets hotter and denser. Soon it becomes hot enough to ignite a new round of nuclear fusion. This time, the star begins to fuse helium into heavier elements like carbon and oxygen. It's like a cosmic recycling program, with the star using one element to create another, all in a desperate bid to stave off its inevitable end. This process continues, with the star creating heavier and heavier elements. It's like a cosmic forge, with the heart of the star becoming hotter and hotter, and the pressure becoming more and more intense. Eventually, the core becomes so hot and so dense that it begins to fuse elements into iron. It's worth noting that the creation of iron in a star's core is a turning point. Iron, you see, is an element that requires more energy to fuse than it releases. This means that the star can't get any energy from fusing iron, like it did with lighter elements. This is the beginning of the end. The star's core is now full of iron, a dead end in the fusion process. It can't create any heavier elements to release energy and balance out the crushing force of gravity. The core is now a ticking time bomb, a dense ball of iron just waiting to explode. But stars can't fuse iron into heavier elements, so what happens next? Well, that's a tale of cosmic proportions, one that involves supernovae, neutron stars, and black holes. But that's a story for another time. For now, let's marvel at the incredible journey of a star, from its birth in a nebula to its transformation into a red giant, and its eventual death in a blaze of glory. It's a reminder that even in the cosmos, there's a cycle of life and death, a rhythm to the universe that's as mesmerizing as it is mysterious.
So, the star has run out of fuel and can't fuse iron. Is this the end? Not quite. In fact, it's a new beginning. A star's afterlife is a fascinating tale of transformation, a celestial metamorphosis that can result in a variety of outcomes depending on the star's mass. Let's start with smaller stars, those with a mass less than about 8 times that of our Sun. These stars enjoy a quiet retirement, so to speak. When they've exhausted their nuclear fuel, they shed their outer layers into space, creating a colorful nebula. What remains of the star shrinks down, becoming a tiny, hot, dense object known as a white dwarf. White dwarfs are fascinating little things. Despite being roughly the size of Earth, they contain about as much mass as the Sun. That means they're incredibly dense. Imagine, if you will, a teaspoon of white dwarf material. It would weigh as much as an elephant. These white dwarfs cool and dim over billions of years, eventually fading to black. They become stellar remnants, cosmic fossils, if you will, of a star's vibrant past. Now, for the more massive stars, the finale is far more dramatic. Stars more than about 8 times the mass of our Sun don't go gently into that good night. Instead, they go out with a bang, a supernova. When these stars exhaust their nuclear fuel, the pressure in their core drops and gravity causes them to collapse. This collapse triggers a violent explosion that can outshine an entire galaxy for a short time. The aftermath of a supernova depends on the original star's mass. If the star was between about 8 and 20 times the mass of the Sun, it leaves behind a neutron star. These are even denser than white dwarfs. A single sugar cube-sized piece of a neutron star would weigh about as much as Mount Everest. If the original star was more than about 20 times the mass of the Sun, its core collapses completely, forming a black hole. These are points in space where gravity is so strong that nothing, not even light, can escape. They're cosmic vacuum cleaners, sucking up anything that gets too close. And so, whether as a white dwarf, a neutron star, or a black hole, the star's legacy lives on. It continues to interact with the universe, influencing other celestial bodies and the space around it. The star's death isn't an end, but a transformation. It's a change from one state to another, a shift from the visible to the often invisible, but always influential. From birth in a nebula to a potential end as a black hole, the life cycle of a star is a journey of cosmic proportions. And it's this journey, this stellar evolution, that helps us understand the universe and our place within it. Let's take a moment to recap what we've learned about the life cycle of stars. Stellar evolution, ladies and gentlemen, is nothing short of a cosmic ballet. The dance begins with a star's birth in a nebula, a vast cloud of gas and dust. From this humble beginning, stars embark on a journey of transformation, entering the main sequence phase where they burn hydrogen to produce helium and light. As the hydrogen fuel runs out, stars expand into red giants, their outer layers swelling and cooling. But this is not the end. Far from it. Stars then face one of 3 fates, determined by their mass. Some become white dwarfs, cooling and fading over billions of years. Others collapse under their own gravity to form neutron stars, while the most massive stars end their lives in spectacular fashion, becoming black holes. And that, my friends, is the incredible journey of a star, from birth to death and beyond.